Okay, so I decided to re-record this because I made a lot of mistakes. So this is gonna be electron configuration and just a little bit on Coulomb's law. I don't want to go more into that when I haven't done PR trends, and this is mainly how it's gonna be for like I guess structure wise. Like I won't go for like specific topics in general, but like I'll generalize it. So like if like it's relevant to what I'm talking about, then I'll like talk about it. So for example, like for like equilibrium, like if I talk about the formula, then I'll talk about like everything else, like how I use formula, everything else. So it could be like 7.1 to 7.5. Anyways, that's just how it's gonna be. So for legend configuration, just like Clyde talked about, there is it's the orbitals, like the amount of orbitals in a specific shell, and it depends on how many, like what energy level it is in. So for example, let's look at carbon. Carbon has 6 electrons, right? And it has 2 shells. And this would be, by Bohr model, this would be 2 and this would be 4, right? But as you all know, there is the S block, there's the P block, the D block, and the F block. Those are the 4 main blocks. F block isn't really talked about in the AP. That's like super confident. So for you guys, you need to focus on these 3. So for here, just to recap everything, the S block always has 2 electrons. P block always has 6 electrons. D block always has 10 electrons. That's like the maximum it can hold. So in carbon's case, if we do the configuration, his configuration would be 1s2, 2s2, 2p2, and there's obviously you should use the class said the diagonal method, but you'll get to a point where you'll just know like how to find it like immediately, and I'll go a little bit more in depth like how I do this. But anyways, this is the main setup of the whole models, and this is many many concepts behind this, and I'm just go through some of them. There is Pauli's exclusion principle, which basically she said that he says he should. I don't know who he is, but basically to summarize it up, every like orientation has 2 electrons per and for example, you know how P has like Px, Py, and Pz, and like they can only hold 2 electrons per. So like you have like this, like only 2 per. That's basically that she basically found it out. It's called Pauli's exclusion principle. And so that's basically what she said. 2 electrons has to be per, I guess I'll call it like per orientation, whatever. So, right, if we look at, let's put a picture right here. Here, right, this is how many, I guess, sections there are per orbital. So for the S block, since it can only hold 2 electrons, there's going to be 2 electrons per. Since P, since it's 6, there'll be three orbitals in the P block, each holding 2. For the D, since there's 10 they can maximum hold, it'll be 5 orbitals, and the F is 7. So what we can do about this? Well, we use how we place them is by Aufbau's principle, just follow diagonal method. But this is kind of important because this kind of tells you the energy, like the energy levels. So it says that you pair the least amount of energy first, and then you just kind of go up, right? So in this case, right, carbon, this will have the least amount of energy, this will have the most amount of energy, because based on this principle, because this is at the very end, this will have the most energy. And this can really tell you a lot about some electrons, and maybe some FRQs or even some questions will tell you like, oh, which orbital has the most energy, and then you would say, oh well, the P orbital in this case because it is the last one, or because since it's farther, there's a whole reason for it. But just put in simple terms, it's at the very end, and because Aufbau's principle, you pair the least energy first, and then like the higher energies, this one will be the most, because, and it really makes sense because again, you have your electrons here, and the closest ones, they won't really use a lot of energy, but because of the repulsion that happens with the other shells, they'll start gaining more energy. And now the question is, well, what about the S block and the P block? Because they're in the same shell. Well, again, you pair the S blocks first. The S blocks are more of like, kind of like, I guess you can call them core electrons, because they're kind of, let me not say core. They're like the I guess the closest one to the nucleus, right, in each cell. So since S is before P, right, this will have less energy than this. That's between shells. Now, obviously, if you have like 2P and 3S, well, this will have more energy because it's in a higher shell, and because in a higher shell, there's more electron repulsion, so that just means that they'll have more energy. Now let's go through let's just write some configuration for some compounds. So let's just start off with like phosphorus. So another thing is, let me actually bring this over. Okay, I'll get this. So yeah, so let's look at phosphorus. Well, phosphorus, by the rule, or actually, let me not use the rule so that you guys can understand what's going on. So a bit of more explanation. Let's just make this into like kind of a diagram, right? This whole side, and I'm sure you guys know this already, this whole side is the S block. This whole side is the P block. Also, helium is part of this, is part of the S block. This is part of the S block. This in the middle, let me actually just make it different colors. Just put like a wall here. Let's put a wall here. This is your P block, except for this. This is your D block. And this is your F block. I don't want to go into the F block yet, but that's basically your entire structure of the electrons and everything. Now, a good way you can visualize this is you can just start pairing like which ones are which. When I'm gonna explain what that means, right? This is the first shell, so this will be 1s. This will be 1s, right? The second shell, so these will all be 2s, 3s, and I think you understand. So each period here is gonna be, everything. So this one would be, sorry for my handwriting, but I think you guys understand like what I'm talking about. So this would be 3s, 4s, 5s, 6s, 6, 7s. Anyways, now here, exact same thing, except you don't start at 1s. This is second period, right? So this would be 2p. This one will be, smooth this real quick. This one will be 3p, 4p, 5p, 6p, 7p, yeah. 5p, 6p, 7p, right? Now it gets more complicated when you get to the D blocks, because the D blocks, you think it's 4D, but it starts with 3D. So this whole row, I don't know where I should put it. Let's put it like right here. This is 3D. This row is 4D. This row is 5D, and this 6D. And then for this it's just 4F and 5F. So this one's 4F and this one's 5F. So with this, you can kind of visualize what the structure would be, right? So now let me just bring an example, right? If you choose phosphorus, right? Let's look. All right, let's see what electrons. So it is at the third row, right? Meaning that its electrons will be in here, and it'll be here until at the end, right? Until you reach electrons. So now we can kind of go through it. Well, let's look at the first cell. Well, it's fully filled, so we have 1s2, right? And then for the second shell, S is filled, P is also filled. So 2S and 2P are also filled. So you have 2S2, 2P6. And now we look at the actual, like, regarding the actual valence electrons, I guess you can say. And by the way, it's, you guys know at the outermost shell is your valence electrons. So that's just, how it is. And if this is bad, like, this might be a little, like, kind of confusing, but just, this is just like how, like, you can kind of visualize. And this doesn't, you won't really need this until you get to really the D block, because D block is where it gets complicated. So anyways, P is in the third shell, so we can see that it has, its S block is filled because it has enough electrons. But now here, let's see, where is it? It's 1, 2, 3. So it's 3. So out of this whole P blocks, remember, P can have 6 electrons. Right, I'll just put E minus. That's electrons. Since the P block, let's put the P block. So the P block can have 6 electrons, right? This one only has 3 in the P block. So for the exponent, if I assume y'all can already assume, it will be 3P. P3. That's would be phosphorus, and that's kind of how you can visualize it. You guys will probably get to the point where you guys will do this so much that you guys will basically already visualize this. But if you want, you can, like, I guess you can take a picture of it or whatever. You can search it up because I'm pretty sure it's out there somewhere. But this is kind of just the visualization of which electrons are in which orbital for depending on the periodic table. So now let's go through transition metals, because now let's actually use like this D block, right? Let's look at cobalt. So for cobalt, let's start with what period is in. Well, it is in the 4th period, right? So we can do the whole configuration. So start with the S block in the first shell, then go to the second cell, go through all the configuration, or we'll use the condensed form, or the noble gas form, she calls it. Condensed form, same thing as you take the noble gas before. So in this case it'd be argon because it's before cobalt. If first let's rewrite phosphorus. Phosphorus in noble gas form, we check what is the noble gas before it is neon. So in brackets we put Ne. Do not confuse this with concentration. It's completely different. We put this in brackets and then compare them. So neon's gone, so now we can focus on the actual shell. There's 2 here, 3s2, and then we count here. There is 1, there's 2, there's 3, so it would be 3p6, and just by how I explained it earlier. Now for cobalt, it will be argon as the noble gas. So for CO, we can put this in the brackets, and then we can count. So now we're at the 4th shell. So 4th shell, let's see. 4th shell, its electrons are filled because it has more electrons, right? So it fills its 4s block. It fills the 4s block. Now what about this block? Now here, right, we can count 1, 2, 3, 4, 5, 6, 7, right? So now this has 7 filled in the D block, and this is kind of why it's good if you remember that this is actually 3D and not 4D, because now you counted how many electrons are there, and so now you can just put 3 4 is 2, remember the 2, 3D7, because there is 7 electrons in the D block. You can count it. So this would be 1, 2, 3, 4, 5, 6, 7. I counted already, right? And this is a really easy way. This is really simple. You guys should probably learn how to do this. If you guys didn't understand it, ask me. I'll see if I can clarify some things. But this is probably really important because you don't want to go use the diagonal method, count the amount of electrons it has, and start subtracting, because that takes a long time, right? And it goes for any of the elements. So for example, if we're going for PT, right, you're gonna go through every single one except for here. You'll fill the 3D, then the 4P, then you'll fill this one, then you'll fill this one, and then this one. And you go to the next shell, you'll fill this one, you'll fill this one, you'll fill this one, and then you go to the end. If it's if you're asking for the full state, the full electron configuration state. So let's do that for let's do with W. I don't know what W is, but it's pretty whatever, right? So now we look, it's in the 6th period, so we can just kind of fill everything out before it. So we start with the first shell, then the second shell, 2s2, 2p6, then the third shell, 3s2, 3p6, the fourth shell, 4s2. Remember that there's now a new set of orbitals. So, and remember 3d, so 3d10, 4p6, then 5s2, then 4d10, then 5p6. And now here, there is the length aside, so I'm not gonna get in depth of that, but you'll just fill the whole orbital, then you go to the, because remember there's this thing here, but I probably shouldn't have went to 5G. They won't test you on the elements all the way down there. So this would be 6s2, then you fill the F block, so it's 4f14, and then 5d, I believe it's 3 actually, because there's this one doesn't really count. Yeah, it might be 5. It should be 5d. Anyways, that's just how it's gonna be. So that's kind of the thing in a nutshell. But yeah, so now just give me give me 1 second. So now, right, when we go with the ions, you will if it's not a transition metal, then you'll like just kind of, for example, if it's like C plus, then my brother's walked in, my bad. But if the C plus, then again, remember, if there's a positive charge, then you're losing you lost some electrons. If it's a minus charge, you've gained some electrons, right? So for let's use silicon. So if it's Si plus, then that means that silicon lost its it lost one electron. So instead of it having 14, it'll have 13. And you can just visualize it. So if it has 13 electrons, it's be the same as this, or you can write the entire configuration, just subtract 1. There's 2 different ways. We'll put both ways. So let's do first with referring it as aluminum. Remember, Si plus has 13 electrons, so it'll basically have the same configuration as aluminum. So for Si plus, and I'm just going to do it in noble gas form so we don't spend a lot of time in this. It will be neon. Then we look at the orbitals. So it's over here. It's over here. So we know that the S block for the third shell is filled. So 3s2. And then we see that because it lost an electron, it will have 13. So now it's in the P block, and it only has 1 electron in the P block. So this will be 3p1. And this really goes for anything else. If I do Cl minus, then this would be, I think you can just put this, right? But let's not do it like that. Actually, it's kind of, I don't think you should do it like that. You do neon, and then you fill the shells out. Remember, Cl is over here, meaning that that your S block is filled. So 3s2, and then you have 3p, and then we check, right? So normally it has 17, but because it's Cl minus, it gained 1 electron. So because it gained 1 electron, it will be 18. So instead of it being 3p5, it will be 3p6. And this makes it stable because its electrons are full. Now, this is for non-metals and nothing that are transition, because transition metals are when it gets kind of tricky, right? So let's do, just like, I think pretty sure we have like an example on this, but for now let's use Ni, nickel. Yeah. Now if I do nickel 2 plus, right? What happens? Well, let's kind of, draw things. And for the transition metals, for the ions, it's better if you make the regular one first, meaning that you don't like ignore the ion for now, and then you determine which one it's gonna happen. And obviously, if it's minus, then it's kind of easy. You just add the electrons. But if it's plus, it gets kind of a little complicated because remember, instead of subtracting for the 3D, it's by the 4s. So for Ni, this would be in condensed form. It'd be Ar, and then you'll have 4s2, and then 3D is at 7, so 3d7. Oops, my bad. That's cobalt. 3d8. Now, because you're losing 2 electrons, we take away 2. We remove 2 electrons. Now the question is, which one? And most of you guys already know, we take from the S block because it has more energy. So, and for those people that are that know that this isn't actually true, just don't worry about that. Just like for AP Chem, just know that the 4s it'll have more energy. So you can that's the one you remove. So we remove these because it's 2 plus, so we move 2 electrons, and now your electron configuration will be 3d8. And you do that for mostly every single transition metal, and you're basically done. That's basically how the electron configuration works and how everything really happens. Now, for the diagrams, because now we're gonna the diagram is really important because that's also that's probably most likely what you'll get on the test. So you can just use an example like probably phosphorus, right? And phosphorus has 15 electrons, right? And so as a configuration, I'll just leave it to you guys to write it while I erase this. If you guys have a pencil or anything with you, or you can just kind of just memorize it and just say it out loud. But P is in noble gas form. It has an E, 3s2, 3p3. Yeah. So now let's kind of make the diagram for this. So again, remember in the S block, there's always one, suborbital. So you have your S block, 3s. What's happening? Let me actually write in the lower thing. You have 3s, have the things. So we put those first because it's in one orbital. So we assign the electrons. It will go in 2 different directions. Remember, always goes in 2 different directions. And now we put the P. Now the P, if you guys remember, there's 3 suborbitals. So I put the 3. Right? And now, right, as doctor said, you always assign them in one direction first. And that's known as Hund's rule, where you always assign electrons in one direction before you put the other. So this is kind of the diagram that you would make if it's phosphorus. And obviously, if they ask you for everything, then you write the 1s, and then you put the two directions, and then you put the 2s with this, and then you put the 3px, 3py, 3pz. I mean 2x, 2py. It's my bad, my mistake. 2px, 2py, 2pz, and then you'll just have, you'll assign them in one direction first, and then you'll put the other one, because there's nothing. It's enough. So that's how kind of to go through it. I kind of didn't mess your handwriting because that's not really useful. But now the problem comes when you look at transition metals, and she kind of covered this yesterday. But for transition metals, they like to follow the half octet rule, and I want to emphasize this. This only applies to transition metals. This does not apply to anything else. If you have like Cl, you can't you can't make but I can make this go into the P block and S will be half full and P will be full. That doesn't work. It's only for transition metals. It's only applies to transition metals. So and the two that really follow this is this and I believe it was this one. These are two ones that follow it. And again, ions also participate in this. So if you have Fe2 plus, or if you can find if it can cut it in half, then it will cut it in half. So I'm gonna do an example with Cu, and then I'll do an example with an ion. So let's look at copper. So first, I'll just let you guys give a few seconds if you guys want to write it down. Write out the configuration of Cu. Give you 10 seconds to do that, or just pause it and just write it down. So we look at it. Let's put it in condensed form. This is gonna be Ar because that's the lowest noble gas. Then we go through. Well, Cu is here and has enough electrons. It will fill the 3s block, the 4s block. Sorry. And it will put 9 here. And to kind of visualize this, let me just bring this. Let me just bring this to here. If I know how to do that, paste. Oh, it's black. Okay, whatever. Can you guys see that? You can see that. Okay. So let's kind of visualize this. So let's use the diagram now here. You have 4s here. And let's make the arrows. And now, if you guys recall, 3D has 5 orbitals. I'm not gonna write this the subscript. It's just 3D. It's just 5 of them. There's different subscripts. That's it's like x minus y squared. It's kind of 3-dimensional. But I'll just put 1. I'll just put 3D1, 3D2, 3D3. So 3D1, 3D2, 3D3, 4, 5, just to kind of represent that they're different orbitals, right? So we assign one direction first, and then the other direction, and we leave off with one left. Now for transition metals, this electron will jump to here. It will jump. So how that will look is this will be erased, and this will be here. And this is how it would look, because for transition metals, half full also is semi-stable, and it wants to be as most stable as possible. So let's kind of look at how the structure is affected, right? And let me just re-erase this and let me just rewrite it. So for this, again, because this 4s jumped, this 4s now only has one electron left, but the 3D is full. So that's kind of how you can kind of visualize it, or you can see if one can be fully full, one can be half, then you can show the configuration. And this could appear in the AP, just the configurations and like these changes. And again, this only applies to transition metals. Do not try to do this with the non-metals or like any of this or any of these like the elements of the P block or anything there. This only applies to the transition metals. So let's look at ion. So let's look at iron 2 plus. So how we write iron 2 plus, we use the condensed rule or the noble gas form because I don't want to write all that. This lowest noble gas is Ar. And then we see that Fe has enough electrons, so it will fill the 4s. And then let's first do the original one, and then we can work on it there. So this will be 1, 2, 3, 4, 5, 6. This will be 3d6. And now, if you can see, now we check with the oh my god, we check with the ion, right? So again, we lose 2 electrons, and therefore just give me 1 second. Okay, I'm pretty sure this is a good learning process for me too, because I need to see if this is actually true. But that's why I was searching it up. What about if it's... Does this apply to iron? Actually, yeah, I don't think... This is my mistake. I mean, I think I would think it works like that, but I guess not. But just know that this one will be... These two will have that, like, that jumping. So next is pretty... I'm going to have to search it up, actually. Is what we call it's called photoelectron. Photoelectron spectroscopy. I'm just trying to find a graph. Yeah. So the graph will kind of look like this. And yeah, I'll just use that. It doesn't have the numbers. So yeah, actually whatever, it doesn't matter. Let's take the photos and let's import it over here. it's not showing up. My bad, guys. Just bear with me for a second. Let me just paste it actually. Oh my god, it doesn't paste, bro. Okay. It's the wrong thing. Oh my god. Okay, whatever. I'll just draw it. So basically your graph is gonna look like this. You'll have this, you'll have the two lines like here, and you're gonna have kind of jumps like this, right? And I'll probably like just leave it like this, like this, like this, and then let's put one more, right? And this is pretty important, but this is kind of like your like relative amount of electrons. So for example, they'll probably be like this, and then like this, right? And so you'll have like 1, 2, 3, 4. You can count it, right? But this one, this one will have energy, right? And it will start not from 0. This is the graph. This graph will not start from 0. This graph will start from 1,000, 2,000, something like that, right? And how this pretty much works is what basically, just to make simple things short, they undergo some thing where the electrons are like basically emitted with light to the point that they will bounce, right? They will go far, or they'll go depending on how much energy it has. And no, actually, let me rephrase. Based on, I guess, how close, for example, or like I guess I would say like the forces, right? How much force I guess it needs, or how much energy I guess you can say. So for this is I'm like, I watched one video on this. I'm trying to explain it, but I'll go more in depth the next like video. But basically, what you need to know is the electrons closest to the nucleus, they will not go that far, so they will bound and go here, right? But the ones farther away from the nucleus, they are the ones that will go far, right? And some people, you guys can probably assume that this kind of allows you to determine the orbitals, right? So if we assign numbers here, we can identify what element this is based on how many electrons jumped. So these are the closest ones, meaning that these are close to the nucleus. We can assume that these are the 1s block. We can see that it goes up to 2, right? So S block's filled. And what's next after 1s? It is 2s. So we can assume that these electrons, they have more energy than 1s, but they don't have a lot to the point that they won't go that far. So they go here. And we count again. This has 2 electrons. Let me just and so there's 2s. There's 2 of them, so this will be at 2. And for here, we can assume that this will be the p block, because it goes super far and it has more energy than 2s. This will be 2p. Now, how many electrons are there? If you can look, there is 4. So now, let's identify what element this is. Well, we'll write the configuration. So we know that it is 1s2, 2s2, 2p4. Oops, not 2. Yeah. Actually, yeah. 2p4. So now, we look over here. Which element would that be? Give you guys about 10 seconds. It would be O, because O has 4 electrons in its p block, and it has the 2 and the 2 and the 4. And this is basically the questions you'll get from it, and it will tell you like which ones will energy. Let me pull up an actual like graph. Yeah, it'll kind of look like this, right? And that's kind of, you know, let's actually like do this question actually. This would be a good idea. Oh my god, I have to show the pictures. Let me just take a screenshot. Okay, so now here it asks you the binding energy per electron, and this is what I mean. The ones that have it will not start. It's not going to start from 0. It's going to start from, you know, the most amount to the least amount, and this gives binding energy, which means that it's basically how easy it'll give off its electrons. And this kind of makes sense because they will not like the electrons closer to like the ones closer to the s block. They're not gonna go that far because they're more close to the nucleus. They have more force of attraction, so it will take more energy to give off that electron. So that's why when you slam light with it, it will not go as far. It will only go up to here. So let's just write, you know, the question. It says to write the ground state electron configuration of the element. And for here, don't get tricked. These they're in intervals of 2. So this is 2, this is 4, 6. And just to figure that out, you know, the S block can hold 2 and this, or like yada yada, right? So kind of you have to kind of look at the graph and see, you know, how many intervals is it in. Normally it's always in 2. It's always in 2 intervals. So the first line will be 2, or be 4, or it'll be intervals of 1, where the curve will go up to like for example, it'll be like this, and then like the curve will be 2 points, and like you'll have the things with the p block like that, right? So let's kind of go through it. So the first one, this is the first, you know, energy level, but this is 1s. You can see there is 2, so 1s is filled. Second one, you can see that 2s is filled, and we can see that 3p is also filled because it goes up to 3, and we know that it's intervals of 2, so this is filled. Next, 3s is filled, and 3p is also filled. Oh, where'd it go? 3. Oh my god. 3s2 is filled. 3p6 is also filled, and at the end it goes up to 4s2. I don't know why it keeps. I don't know why it keeps doing that, but it goes up to 4s2. Hopefully you guys understood how I found that out, and for this purpose I'm just going to rewrite this configuration. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Now the second question says identify the elements, and now since we know the configuration, this is pretty easy. So let's look at the periodic table, and based on the knowledge I've said, again, its highest thing is 4s2, so we check which one is a 4s2. It is calcium. So this element has to be calcium. So the element has to be calcium. And that's basically it for full electron spectroscopy and electron configuration. So next, by the next video, we'll talk about Coulomb's law and periodic trends, and we'll finish off, maybe we'll probably finish out unit 1, and then I'll answer, I'll just get like a good 20 questions of unit 1, maybe also an FRQ, and then I'll make kind of like a test for y'all to see if you guys understand what's going on, and depending on that, I'll go more specific and try to help you guys out more. So that's basically it.